Let f be a polynomial with real coefficients and degree n. Let's prove that f has at most n minus 1 local extrema, whether they're local mins or local maxes. The idea of the proof is this following statement from Calculus 1, that suppose we have a function that where f has a local extremum at the point c. Then there are three possibilities. Either c is an endpoint, or else f prime of c is undefined, or else f prime of c is equal to 0. So if it's a local extremum, then one of those three things must happen. However, the reverse is not necessarily true. In other words, if f prime of c is equal to 0, that does not necessarily force that c is a local extremum. And a typical counterexample for this, the most typical one, would be x cubed. So if you take a look at y equals x cubed, then y prime is equal to 3x squared. So that y prime of 0 is equal to 0, so that 0 is a critical point. However, the graph of x cubed goes like this. So there is a horizontal tangent line at 0, but 0 is not a local min, and it is not also a local max. So anyway, but this theorem does hold that if it's a local extremum, then these three things have to one of these three things has to happen. It's an endpoint, the derivative is undefined, or the derivative is equal to 0. In our case, the function f is a polynomial, and it has domain over the entire real line. So where there are no endpoints, the function is defined over the entire real line, and there are no places where the derivative is undefined. So therefore, the only possible extrema are the places where f prime of c is indeed equal to 0. Now, that's interesting, of course, because the f prime of c is equal to 0. F is a polynomial, which means f prime is also a polynomial. Indeed, f prime is a polynomial of degree n minus 1. And therefore, if we try to solve the equation f prime of x is equal to 0, there will be at most n minus 1 real solutions of that equation. We are guaranteed n minus 1 complex solutions if we count multiplicities. So we could have non-real solutions. We could also have multiplicities. So because of that, we are guaranteed at most n minus 1 real solutions, though we are guaranteed n minus 1 solutions if we count both multiplicities as well as complex numbers. Okay, so there are going to be n minus 1 places where f prime of x is equal to 0. Those are the only places where f prime, those are the only places where f could have a local extremum. Of course, not all of those will cause a local extremum, and so that leads us to the conclusion that there are at most n minus 1 local extrema of f. And so that's the proof of the theorem, relying on the unique factorization theorem for polynomials, as well as this theorem from calculus about where the local mins and maxes of a function applies, and therefore where the local mins and maxes of a polynomial can be found. And so that is the end of the proof.